Okay, let's start today's hep-ph seminar. Today's speaker is Seung Lee from Korea University. He will talk about the interesting topic, continuum dark matter. Please start when you're ready.
Okay, so thank you so much for the invitation. So yeah, it's very nice to come over here, even though it doesn't take more than 10 minutes. And actually, I plan to visit here more often next semester when I have more postdocs and students. So anyway, today's title is Continuum dark matter. So this is the thing that I've been working on recently. And I didn't even write down all the project I'm working on, but there are like 3 papers coming out, and the other 2 will come soon. This is the outline. I'll give you some kind of general introduction and talk about what is this continuum and what's so special, and then like tell you how to compute this continuum. Because continuum is like not a particle, point-like particle, right? Resonance. So it's different from just calculating some new particles. And I can talk a little bit about how to do the computation for thermodynamics and the dark matter. And then I'll give you a nice toy model and show why this is interesting. And I will summarize. So yeah, I mean, we're all motivated, right? Basically, like all of us are doing something very fundamental. Like it's very interesting. We can ask this kind of question using physics, right? And how do we get even here in KIAS? Like, for example, I mean, there are many ways to ask questions, but like, first of all, like the dark matter. Without dark matter, there wouldn't be any galaxy formed or stars, so we wouldn't be here, right? Because there will be other questions like why we are here instead of being empty space. But so the outlook of dark matter. So dark matter is the most important question in particle physics, because I would say theoretically, like there is like naturalness question, very interesting, but unfortunately, like so far LHC hasn't found anything yet. So we have to wait maybe for next generation for LIDAR. And also that is more like a theorist problem, not experimental problem, but dark matter is a real thing. So something must exist. So that means there must be BSM. So this is like an old picture of outlook of dark matter, and a lot of things are WIMP, but the recent snow mass, okay, now it becomes even in dark matter, after like you didn't find Suji or anything. And more importantly, last 2 decades, a lot of efforts are going on for direct detection of dark matter, which never, and which also failed. We didn't discover anything. So now it becomes like a democratic and everything can be possible. Dark matter, we have no big idea. Except that, I mean, there are so many detections only through gravitational interaction only. So we know it's there, dark matter is there for sure. But still, this is one of the biggest mysteries. So we don't know the mass of dark matter, composition of dark matter, interaction of dark matter. We don't know anything, right? The dark matter scale can be as small as 10 to the minus 22 electron volts, right? Below that, the de Broglie wavelengths will be even bigger than galaxy scale, so that's not allowed. And the upper limit is roughly like you didn't see micro ranging of the primordial black hole, so it cannot be too heavy. But 80 order of magnitude, it can be anything, right? So dark matter is a very nice, very important question. It's not theorist-made question; it's a real problem. But on the other hand, like if you are like model builder, then it's not too exciting in a sense that the rules are too loose, so it can be anything. So that there are 2 sides of this dark matter. So the idea of this talk is that okay, dark matter is made of an ensemble of some gap continuum. Because like usually we say dark matter is new particle, but it's not even clear whether it has to be a particle, right? So then how about some continuum? But of course, like the gap, having a mass gap is important because otherwise there is no phenomenology. So then like sound like you want to talk about some continuum, which is not a resonance, but with some mass gap. Why do we care? And isn't it too exotic? Actually, it's not so uncommon if you talk to your condensed matter colleagues. Like for example, like everybody knows fractional quantum effect, then their edge state is basically gap continuum. Or there are many other things like 2D IT model or Turing model and 2D Seung and so on. In the Lagian limit, there are these things occur. And it's not also completely new in particle physics. So the appearance of continuum is very common for those of us who run field theory. So for example, in CFT, the continuum arises, right? Because the conformal symmetry does not admit any scales, so there shouldn't be any resonance, and therefore continuum arises. And of course, if you live long enough, you're too young, you don't know even this name, particle by Howard Georgii. So this is another example of gapless continuum. So, and then string theory, for some reason, like groups have actually spent certain amount of time thinking about this continuum, especially gapped continuum that I'm interested in. And he shows that if you have a stack of these three branes on a disk, you can get a gapped continuum. So basically, corresponding to like n equal 4 Suji breaking down to n equal 2, and so on. This is nice because I'm not a formal theorist, so I'm not saying like this is I'm interested in this string theory realization, but I tell you that in the phenomenology side, sometimes you won't have a UV physics motivation. So at least UV physics, you can realize this gap continuum. Because for our phenomenological model, in the end, like we are dealing with effective theory, right? You cannot talk about quantum gravity and so on. So this is motivation. And also in particle physics, gapped continuum is, I'm not the first one doing this. So there is something called software model. So everybody knows like this like Randall syndrome model, like having two hard brains and the ADS space in between. But then like you remove the IR brain and then replace it by something called software. Then you can have some kind of gap continuum. So people look at this for the Higgs with small mass gap, but this was before Higgs discovery. So people assume that maybe there's no resonance and this continuum first arise and then there's the resonance and they mix. But after Higgs discovery, so this is ruled out. But then I also worked on a little bit on this something called quantum criticality. After finding resonance, I was thinking about with my collaborators what happens if there's continuum after resonance. That can be also realized in this 5D toy model, and that corresponding to like a very interesting off-shell form factor Higgs physics. So mostly people working on on-shell EFT, but you can talk about off-shell EFT. There's like a B physics, like a lot of form factors, non-trivial shape. And also there's another thing that I worked on, so-called continuum naturalness. So basically, the top partner is basically continuum, gap continuum. In that sense, you can hide it a little bit from LHC, and maybe you have to look for high-Rumi LHC. But in this talk, nobody has done is what nobody has done is what about dark matter being a gap continuum? So that is something new that I worked on and still working on. So what is the gap continuum instead of ordinary particle resonance? So you can think about spectral density in Kallan-Riemann decomposition. They are like, but in continuum is like in the spectral density, you have this kind of continuum. And the mass gap is, so throughout this talk, I call mass gap mu zero. This is where this continuum starts. And before there's zero. So you have a mass scale. Unlike the usual generic CFT continuum, which doesn't have mass gap. So like, if you want to think about CFT, you have a usual CFT gapless continuum. But what we are trying to do is you deform the IR of CFT. So do the model building such that instead of it going to gapless region, this continuum spectral density is modified such that it goes into zero at the mass gap.
So which parameter changes the behavior of the row of mean?
Yeah, that's a good question. Generic breaking of CFT will just make it discrete term, right? So it's not completely general. So I'll show you how to realize this in the model.
Sorry, maybe this is a related question. What happens if we consider simple scalar theory with qualitative interaction? Qualitative.
Qualitative interaction, yes.
Yeah. So in that case, so can you show the spectrum?
There wouldn't be any mass gap.
Mhm.
Mass gap doesn't arise. So there will be particles.
So what?
Unless you write down CFT. The CFT, there wouldn't be any mass gap.
Yeah, I
And
understand.
as soon as you write down, break CFT, there's no continuum usually.
Okay.
So I think that answers your question, right?
So what's the shape of the spectrum in?
So this will be my talk. So how this become like this, right?
Okay.
Of course,
Maybe-
if it's that trivial, then everybody would have worked on that, right? It's
maybe
okay.
I will ask.
Yeah.
So I think here, so for a scalar theory for a particle with a mass, this picture would just be a delta peak
Yeah.
at the mass of that particle.
But what I care about just interaction, qualitative interaction. If we add interaction,
The interaction is not modifying this picture at all.
but 5 to the 4th, just very simple model.
So you're talking about some CFT theory, right? Some conformal theory.
Not exactly safety because
And then what do you mean by quality? Which?
just 5 to the 4th.
Yeah, then that is a particle, right? Either massless particle or you can give a mass. So it has nothing to do with spectral density. I thought you were thinking about some theory of some model of CFT where you break CFT with some marginal operator, but otherwise, I think
Okay.
yeah, we can move on.
In my understanding, even in the existence of interaction, we can perturbatively calculate the spectra.
So okay, if you open Pashkin shredder, there's particle, but there is two particle and particle, multi-particle
Yeah.
state. At the root level, you generate this.
Yeah.
But here, okay, I see. So now I understand where you're coming from. Very good. So in particle picture, this happens, but at the root level, right? So usually you have delta function,
Yeah.
and then at some point, 2 particle, and then 3 particle, 4 particle. But here I'm talking about the 3 level continuum. So this is
Okay.
of course, this one will also, if there's interaction, this continuum will be modified a little bit. That's non-trivial task. So yeah, okay. So I hope this.
Is it like ensemble average with different means? Are you going to write down Lagrangian? Or
Yes, very good question. So yeah, so I'll come to that. So that is very relevant question. So I hope at least I give you some of your attention because like, otherwise nowadays, if I give my BSM models, only small number of people got interested in, and other people will say, yeah. So like let's look at the continuum field from just field field. So this is like a scalar field. I can put this sigma. Sigma is basically determined by 2-point correlation function. Or for fermion, you can do this similarly, or vector like this. And basically, if you look at the spectral density, going into Kalman-Lehmann decomposition, basically, imaginary part of this 1 over sigma will give you the spectral density. So for particle, sigma will be just like a mundane p square minus m square plus I epsilon. And then the spectral density, you put this, then you get the delta function, right? So, but what we're trying to do is we consider the case that there is some strong sector, strong interaction can be captured by the fact there is some non-trivial continuum. This is described by this same effective theory Lagrangian. So let's first focus on scalar fields, because that's easiest, and then I will add vector and fermion at the end. Then this is same thing. And then,
Your sigma is going to be some probably non-local expression.
yeah, that's fine. Actually, the thing that I'm coming from like a SCT community, so for me, like non-local action is very, very, or HQET, it's very common, right? The EFT. So the above effective description is weakly coupled. That's the case I'm interested in, resulting in like what we call the free continuum. So this field, we are looking for this generalized free field. In addition to, we perturb around, of course, to have interaction with standard model weakly by introducing some weak coupling to this phi, and assume that the underlying structure described by this spectral density that I was motivating doesn't change much, resulting in like weakly interacting continuum instead of broken down to discrete term. And yeah, but how do this is sound like more difficult to prove it in 4 dimensions. So but this picture is supported by concrete extra dimensional models. So let me briefly mention some CFT. This is not about CFT, so I only talk about something very well-known things. So Seung stated that CFT theory with continuum spectra do not have a particle interpretation of, I mean, there's no S matrix can be defined. So the interaction leading to a non-trivial fixed point are also essential for producing this continuum spectral of the theory. So by turning off the interaction, the spectrum changes from continuum into that of ordinary particles. I'm sorry, turning on the interactions. And the asymptotic stage defined in the usual manner would not capture the physics of the system properly. So basically, if you want to deal with continuum physics, even in CFT, so how many years and how many people wrote papers on CFT, dealing with this continuum, scattering and the mundane particle physicists are doing things, require new formalism, usually. But of course, that's too much beyond my expertise. And first of all, I'm a formal theorist, and also, I mean, why didn't CFT people develop these things? Because it's a direction that is not so interested for formal theory. Yeah.
If the S matrix cannot be defined in the CFT continuum, then what can we observe by using CFT?
No, it doesn't mean that you cannot observe anything. Like the usual language for particles, resonance, cannot directly apply naively for continuum. So you need to develop new formalism. If this is very important, then I think a lot of like genius guys have done it. But people didn't do it because it's not the main important topics in the CFT, so people didn't work on that.
Then by using CFT, then can we make any no observable?
You can make observable. Everything is well defined. This theory is very
but-
great, right?
Yeah.
And you can still talk about many things, but like if you talk about like producing it in colliders and how to get cross sections and so on, you need to develop a new language, right? That's what I'm saying.
Then
So what I'm saying is, don't worry. Like what I'm saying is that there is no no tools from like people working on CFT. So in general, if you look for CFT continuum, but there is, I mean, CFT continuum is, we know that in our real universe, the symmetry has to be broken, right?
yeah.
That's why nobody cares.
Just the reason why I ask you is maybe you know that if we cannot construct the asymmetrics, then we don't know the interaction rate something.
Mhm.
So just the reason why I ask you is
Yeah. So I'm talking about in general continuum. We don't have a language. Doesn't mean that
just we need to the other
you need to develop the like a new formalism for dealing with this. This is different from like this like swamp friend argument, right? Like S matrix is not defined in the digital and digital, and this multiverse is bullshit. And there are some arguments some people are doing this, right? But I'm not talking about that. So our theoretical description of this gap continuum will just use generalized free fields, like developed in the 60s, and basically I was like motivated by this by Joe Kumagorski when I visited him in Whiteman long time ago. So generalized free field. Let me just briefly describe. So also you can look at this Polyakov skeleton expansion 70s and or Green's work. So basically, basic idea is simple. So CFT is completely specified by a two-point function, and the other contribution vanishes. So if you're looking for scaling two-point function, this will go like usual p scale plus I epsilon to the power 2 minus delta, right? And this can be generalized from this Lagrangian generalized free field of this. And actually, so there is like George was using this for his own particle. The only thing that's different from what we are doing is that the branch cut starting at the origin, the spectral density is purely a continuum.
So could you show that? Are you saying that the two-point function can be written in this form at the bottom?
This one?
Yeah.
Yeah, anything can be written in terms of spectral density. But this spectral density is.
Okay, so suppose I give you that.
This is the spectral density.
Oh, it's just I never seen that one before.
You have never seen, because you are not interested in this.
It's
And
not important. I was asking, how would you write that two-point correlate of their refractional power in terms of that expression? I just don't see it. That's all. What do I do?
this, I gave you the so if I want to just very basic.
So you gave the picture, not the formula.
The picture, yeah, picture you have to compute it. I mean there are, but basically this rho is nothing but imaginary part of the sigma, inverse sigma. And the sigma is this.
So here you just introduce sigma, right?
Yes, this is generally true. And of course, this is defined such that the loop computation, loop
Yeah,
correction,
that's the
all enters into rho. The non-trivial things all captured by rho.
Yeah, if you start from conventional.
Yeah, that's a Color-Norman decomposition mathematically. This is well defined.
But if I understand correctly, you don't consider usual QFT now, right?
The color normal decomposition is correct for any field theory, not just for particle. Particle plus continuum, as you said, in the one loop there is continuum, right? That's captured.
So what we are starting with?
That is like you have delta function plus you have that is like whole, and the continuum is just branch code, right? Yeah. So okay, so how do we compute this, right? So what I'm doing is like so I'll get to the answer, but so I'm modeling this generalized free continuum. I don't know how to compute this actually, right? This is but I'm just using this toy model using ADS-CFT, right? ADS-CFT. So I have the bulk of ADS space in the 5 dimension, and you can start with this metric and A, the work vector. So this work 5D setup. We have these 3 branes. So one localized at, let's say, G equal R. Instead of 0, so you have this UV cutoff of theory. So which is, from the point of view of the gap continuum field, will be a UV brane cutting off the space, ADS space. So it doesn't go all the way to 0, but starting at some R. And then 5D action of the coupled scalar gravity action is just the usual action of this, where this V is just potential. And so the software, so usually what people do is you put another brane, IR brane here, and then that's usually the playground or famous Randall-Sundrum model and so on. But people at some point find that, so actually if you look at the Kaluza-Klein spectrum, like KK stage, their behavior doesn't go like Reggie behavior. So people working on ADS QCD, so QCD you want to look at the Reggie behavior. So then they look at something called software, and then actually you see that happens. And here, like how do I realize this? So instead of putting hardware, you put some scalar field phi with some potential, and then there's bang reaction with the gravitational theory. But how do you compute? So this is developed by Gupso et al. Called superpotential method. And then if you, so superpotential has nothing to do with supersymmetry. He just named it. So, but this is the way that you can analytically solve, including the back reaction in the gravitational coupled system. And if you do this, you choose this point to this specific superpotential, and this is plugged into this potential. Then the solution is that it works better. Basically, it becomes like this. So there is a singularity ys. So you see that if ys goes to this ay, this work vector ay becomes infinite, which like become a brane hardware, and the metric vanishes there. So this is like a naked singularity. So this is basically the software setup. There's a good the good singularity and bad singularity according to Gupso. So he worked on it actually interestingly. And so this is, according to him, this is the good one. And then you see that this bulk profile of this bulk scalar that I put in this gravitational coupled 5D theory, you see that this profile also gets infinite when you reach into this ys. And the ys is not infinite. The point is this is finite, this location in the y coordinate. So in this software, so that's the basic setup. And then, so now let's look for scalar dark matter. So let me put this capital phi. So this is different from the previous scalar field that give rise to this software. Then this you put this into the 5D ADS slice in this software setup. Then the bulk equation of motion is just like this. But this looks very familiar. So if you do the change of variable psi into phi, you do psi, then this is like a really Schrödinger equation actually. This is like what I give it to my sophomore undergraduate students in my quantum mechanics class, right? So one-dimensional Schrödinger problem with potential, right? But of course, like the potential in this theory, you have to compute. So, for example, in this 5D theory, the potential is this. But what I'm saying is that if this G goes to infinite, so here I'm using G as a conformal coordinate. If this potential becomes infinite, then you have a discrete state. On the other hand, in the limit this G goes to infinite, this potential is finite. Then there is a continuum. This like you can understand from this 1D quantum mechanics picture. And so basically in this setup, the continuum begins at mu0. If this V goes to some factor times mu0. If mu0 is 0, then continuum begins at 0. So basically this gap continuum can be computed from this potential that I wrote down, and this is in terms of this ys, right? One may worry what happens if quantum gravity enters there is just singularity. So how do you know your continuum, the quantum gravity will allow it or just break it? So if you ask me that hard question, I have to say I don't know. This 5D theory is only effective theory. And in the end, like if you want to do UV completion to the string theory, I don't know. Like I mentioned, that's why like Gupsa and other people worked on this gap continuum from string theory. But this is just naive 5D theory, random syndrome or this ADS-CFT 5D playground is. So that I cannot say. But if somehow you assume the quantum gravity allows, then you get the continuum.
Sorry, preliminary question. So the beginning you had the potential V of phi, right?
Yes.
And then the second line I get the V of y. And then
You know the Einstein
V of
coordinate and the conformal coordinate.
No, I don't know
coordinate.
that, but,
Yeah. E to the IKY.
there's a V of y, V of z coming from V of phi.
Yeah. You just do the conformal coordinate.
And then the V of z,
Mhm.
it's a summation or it's a derived quantity.
It's a derived quantity. But so
Since you didn't find what V of phi is.
because I don't want to bother you to write down all these one-page equations of the Vy and then transform it to Vg, so I just do this simplification.
Okay, so the V of z can be derived from certain form of V of phi. That's
Yes.
what you're saying.
Yeah. So if you're interested in like the lengthy expression, I can refer it to my paper.
So V of phi is complicated?
Yeah.
How much?
No, it's not that much. You know, as a phenomenologist, I'm not going to spend 1 year on this. Like it's just a one. If you do one day,
Then okay, as
one day,
I
so-
would say that
Yes.
V of z is just I just write down V of z. It's answers, I think.
it's not answer, it's answer, exact answer.
Exact answer.
Yeah.
You have chosen probably some form of V of phi, right?
Yeah. So
Isn't that an answer or is it derived from?
no, it's a model.
It's a model, yeah.
This is a model. Who told you this?
That was okay. That was.
And then everything follows.
Okay.
This is
Can I see
this
the-
setup is the
Can I see
model.
the pre-
Yeah.
W?
W is what people call superpotential.
Okay, so
Because
V from W.
it's not the only form of superpotential, but there are
Okay.
like
hand
hand
Let me try to
forms.
understand myself.
I mean, maybe you
So
don't.
W
If you it's first time you don't know
phi-
what superpotential means. It
Oh,
means
phi-
like you can compute analytically instead of numerically doing. You can.
I'm sorry. I'm the first guy to see this. I never seen this. So W is the function of phi.
Yes.
From that you derive V.
Yes.
It is specified.
Yes. Exactly.
That phi is big phi.
Yeah.
I mean, you exchange notation so many times, it's confusing.
I'm sorry, it's my fault. Yeah. Yeah, and why this specific form? Like, if you don't choose this form, you don't get software.
Okay.
Yeah. So if you think, this is very weird form, why do we have this software and continuum? Yeah, but there's no fine tuning. That's the point.
In that last picture, yeah, there.
Yeah.
So Z going to infinity is where this continuous spectrum sits.
Yeah.
And in that graph,
Mhm.
where is your physical brain sitting? On the left or the right?
The UV brain.
I don't know what UV and I have. Where is your standard model sitting?
Yeah, here.
So all these things are very far
But this is cartoon picture. I'm sorry. This is cartoon picture to show. This is ordinary Schrödinger equation, right? And then the Schrödinger equation, if this potential goes finite, right? And then
I understand.
one side is a wall, one big quantum mechanics that we teach freshman or sophomore students. You have one wall, and then there is a potential, but doesn't go to infinite. Then you have continuum. That's the
I understand.
yeah.
His question is where
I did my Schrödinger.
Yeah. So
I was just
this is a
asking,
cartoon
where
picture.
is your physical world? Where is my case?
Okay, so don't look at this. This is just a cartoon picture of this Schrödinger equation, Schrödinger. So the undergraduate
So
student.
this comes from some version of.
So this is the UV brain or brain. I will say this is brain because before that anything can happen. But let's assume your standard model is here, and then the continuum is leading on all this CFT.
So Z going to infinity is same Z going to infinity in this picture. That was my question.
Yes.
So these continuums propagating far
Yeah.
away from.
Yeah. So the y-axis is finite, but if you go to conformal coordinate, then that corresponds to G goes to infinity, where the singularity happens.
So you are essentially talking about continuum of Kaluza-Klein mode.
Yeah, so instead of discrete term, you have continuum, and only the dark sector is that. And then standard model is living on the brain. But if you care about, what about the naturalness Higgs mass hierarchy problem or gauge hierarchy, you can think about this as IR brain and UV brain, and that's another bulk. And that's a standard model. Or you can think about that as a thick standard model brain. But what I care is beyond that is a dark sector. And this is here for toy model, I just put scalar field. So that is the CFT gap continuum. That CFT is like marginally broken. Like this software. Yeah. So I'm sorry for like not really capturing your question, but are you happy now? Yeah. I mean, at the beginning, I didn't get your question, so. Okay, so let me go. So what I'm saying is that so you need to know how to handle with this gap continuum now. How does it interact with particle? And why do you care that this gap continuum is a dark matter? Is it interesting? Okay, so nobody thought about this gap continuum as a dark matter before. That's new, but I would say that there are many more exciting features coming out of this. But even before getting into the answer, let me advertise one very good effect of this dark matter being a gap continuum. As I told you at the beginning, if you go back, like a time machine is there. So if you go 20 years ago, you see that most of people are talking about WIMP dark matter, right? Maybe some people talk about still some part that can be action, but why this is no longer as popular? Because the direct detection experiment cannot find any WIMP dark matter yet, right? So a lot of parameter space is ruled out, not completely ruled out. But if you have dark matter, weakly coupled dark matter to be get continuum, you find that there is some kind of huge suppression, some kind of some rule that makes the direct detection, the cross section very, very small, such that this guy is not, this weakly coupled WIMP miracle is not ruled out at all for if you replace particle by this gap continuum. That's the motivation, one of the very important motivation for the theory. So, but continuum dark matter can be anywhere, of course, right? So, in fact, if it's very light, it's very interesting. How does it affect the structure formation of our universe? That's interesting. Actually, I'm working on things like this with my cosmology friends, Marco Simonovic, and so on. But for this talk, let me focus on this WIMP, weak scale.
Are you talking about mass of the continuum dark matter as the mass means the mass gap size?
Yeah, around the mass gap. Yeah, still there's mass scale, right? That's important. If there's no mass scale, then there's no phenomenology. If you're a phenomenologist, you know that. Everything, the theory would be immediately ruled out if there's no mass scale in your theory.
If the mass is very light, it's like a wave.
It's just still continuum, quantum space. Yeah, but
It may not be a wave like.
yeah, the de Broglie wavelength of small mass is large, right? So it's the wave-like behavior becomes more interesting. But for this talk, I'm looking at the mass gap around the weak scale. So basically, the WIMP miracle everybody knows, and since it's in Korea, I put Benjamin Lee and Steven Weinberg, and they get this number density evolution, and they all found this basically, if your annihilation cross section is larger, then you get the smaller relic abundance, right? So that they found this, but actually they are not the first one. Actually, George did it before, but anyway, it doesn't matter. So this WIMP miracle is a very long story, and still this is the most motivated one. Why is it? Because one thing is very nice, other than just you just put weak scale and then you get the right relic abundance just for free. There's why this is another reason is like this summer freeze out scenario of the WIMP. It's basically insensitive to the initial condition of the universe. Why? Because it started from the equilibrium, so you don't care initial condition. Because the dark matter standard model gases in the early universe will be in the thermal equilibrium. And then, as I said, the relic abundance is proportional to the inverse of the annihilation cross section, which was computed in the 70s by Weinberg and Benjamin Lee. So this is nice thing. Yeah, maybe I should skip this. But the problem is like the usual WIMP story is ruled out by experiment. And right now, so basically Moore's law works in dark matter direct detection business. But still there are some parameter space left, right? I guess for like Suji dark matter searches. So that's why people even talk about future collider dark matter searches. But they are very fine-tuned. The interaction has to be very, very small, and there's some conspiracy to hide it. So we've been searching for WIMP, and so now the dominant paradigm is challenged. So people think about something other than WIMP. But the question is, there another dark matter paradigm that gives qualitatively different signature and still safe from direct detection searches, but give the same level of simple elegance and calculability and compelling explanation for WIMP. So that I hope this gap continuum fit into this category. So let me talk about how to deal with this gap continuum dark matter. So there's no mass, right? So it cannot be on shell, right? On shell means it's being on the resonance, right? So, but still there's mass parameter. So I will denote this mu square to be the mass parameter where this continuum lies in the spectral density plot. So this is continuous parameter and mu zero is where it begins. And then you get some kind of completeness relation, of course, when you do integral of spectral density and this continuum state. Then you get completeness relation, of course. And then question is, how do you compute the production cross section, right? It's very challenging. We have answered, but the best way is if you just using the field theory and use the optical theorem. So basically, you just need to do this optical theorem, take the imaginary part of this, and then you confirm that the production question, for example, 2-to-2 process, can be written similar to the particle physics, except that you have to put this spectral density for incoming mu1, outgoing continuum 1 and outgoing continuum 2, corresponding to rho mu1 square and rho mu2 square. And then you have to do this compute. And that agrees with this optical theorem. So we wrote down this and this was answered, but then we're not sure like this is correct. So we have to check this. Maybe some more smart people will say immediately that this is the answer, but for someone like me, I have to check to see whether this works. So it works.
So so that diagram, so what is, I mean,
So this is a standard model, and this is the continuum.
I mean, I don't know about that part. I mean, if it is the particle, then just particle propagate to one point to
What's
other.
inside? What's inside? Outside is particle.
Yeah, okay.
What's inside is continuum, right? But you don't care.
Continuum.
Yeah, gap continuum. I'm talking about how to produce the gap continuum pair. But how do you compute? Since it's not particle, right?
But, I mean, what means gap continuum pair is not particle, you said, right?
Gap continuum.
I mean,
So experimentally you find something, but if it's a particle, you produce many, and then you see this is sitting like in the resonance, right? That's the particle, right?
Okay.
But you have to do many.
I mean, I'm
Yeah.
what I'm confusing what is the
Yeah.
physical situation which that occurs. For example, yeah, just
It's a quantum state, right? And then
mhm.
whether it's realized as a continuum or resonance, or very narrow resonance, or very broad resonance,
Okay.
still you produce quantum states, right? So there is a production cross section of the two continuum pair. Continuum pair means each one you produce in the accelerator, for example. It's not about particle collider physics today, but if you produce continuum, does it look like it's having spectral density? No. Same for the broad particle, right? If you produce one particle, it can be anywhere in this matter spectral density of this broad spectrum, right? Or if it's a narrow resonance, it should be mostly one shell, right? Continuum, it can be according to the the spectral density. In that sense, is giving you like a kind of the PDF where it will look like, but there's no resonance, no one shell. But you still
Can you go to the previous page? What could be this HI? No, you did right. In the next page, you have this interaction Hamiltonian, which should be like.
Yeah.
So there is a certain.
If you choose 2-to-2 process, you need the interaction term in your Lagrangian, right? Of course, between the standard model and
So I can imagine there is some interaction.
yeah, between fields. not the particle at the level of Lagrangian. There's interaction, right? So it's good that you start thinking about what the heck is this is. Like I give you the spectral density, but spectral density is nothing, right? If this is particle, you have delta function, right? So you always produce something. If it's on shell, then this means it's on shell in the resonance. But suppose you have a very broad resonance, right? Not continuum, broad. If you produce it in the collider, if you have high enough energy and so on, then if it's broad, then which mass will be produced, right? One of them according to this spectral density, right? And still the peak, where the peak is located for spectral density, that is more likely to be produced if you have enough energy, right?
Say one thing, because this might resolve the confusion. So you have a distribution of masses in this density, i.e. if you do one particle collision, you produce two particles out of the spectrum with different masses, and their distribution is giving according to the spectral density.
Yeah.
Same for a collider.
Yeah.
Collider experiment.
It's just a delta function.
I don't know, but my question was even simpler. I mean, I was thinking of what kind of HI I can write.
So this was more
The model building question.
Yeah.
addressing
So you have the gap continuum field phi, and then probably the contact interaction I may write.
So you can just think about effective Lagrangian with a two dark field
Yeah.
and then two standard model. That's it, right?
Yeah.
If this is G total, you
That's
can.
what I guess.
Yeah.
I guess. So if you write this in a 5D model, as 5D interaction, then if you do a standard Klein decomposition, this is giving you a whole tower of interactions between all the different KK states between the two standard model particles. And I'm guessing this is more or less a continuized
Okay, yeah, that's right, yeah.
version of this when you do the decomposition.
So yeah, so I don't want to go down. I don't go directly to the model because then you don't understand where what's continuum, right? So I'm just giving you generic pictures.
Let me change my question then. So in that, for example, why do you consider the loop? Why you don't just more simple case can just tree-level exchange of the continuum?
I'm just talking about pair production of 2-to-2 process because that's the easiest to do the model building, right? The pair production of the continuum
You
sector.
want to calculate the 2-to-2? I mean, two standard model, two continuum.
Yeah. First, like if you want you do dark matter ABC, you first need to compute the production cross section, right?
Then in the previous slide, final state. So no. Yeah, there. Yes.
Yes.
There. Need to. Is it correct?
Yeah, this is the amplitude and
Yeah, the first.
Yeah.
The first formula.
Yes.
In this page. No. Yeah. In the
This is the amplitude.
in the formula, the final state P1, V1 is a kind of state, but it's not particle.
Yes.
Ah.
Yeah. Still, you can define the momentum of the field. Right?
Then how can we detect them? No. Can it detect the continuum?
Yes, I mean, Tom actually told the engine, right? Like this is if you produce it in the collider, we have continuous mass parameter.
Yes.
But when you produce you look at one event,
Yeah.
you produce it in one of these continuum parameter according to the probability of this spectral density is like a probability. Where more likely you find. It's the same for particle. Like if you find only one event, you don't know what is the mass is. What the mass is, right?
Yes. Finally, what we detect is a kind of electron or
Yeah.
just by using the
Yes.
other
Yeah.
very detectable particle, we can track the continuum spectrum.
Yeah, and if you find this many events, then you can generate the spectral density plot. Yeah. So that is how you do discover. Okay, so anyway, so that's how we develop the formalism. And then you can do the similar thing for equilibrium thermodynamics, like number of particles in terms of the space density, and then usually like we compute the free energy and you derive a lot of things out of free energy as usual, and like energy density and so on. You can use in terms of the spectral density. You can denote this. Since I don't have much time, let me skip some details. But the goal is to first you need to find the Boltzmann's equation for continuum, right? So first you have to specify the two-to-two scattering. So that is kind of the you can go beyond two-to-two scattering, but we can have models like this, which is our model. And then this is the Boltzmann's equation, and then you can generalize it to the FRW background, and yeah, you put all the covariant derivatives, and then during the freeze-out process, dark matter is at the same temperature as the standard model T, and has a common chemical potential, which we call eta, because mu we already use for mass parameter. But this is time dependent, and so at some point in the freeze-out calculations, the dark matter will still have this chemical potential, and this, and standard model have this phase space density like this. So in the end, using this, and then I show the Boltzmann equation. So you integrate Boltzmann equation in both sides using this. So you integrate over this mass parameter with spectral density as a weight and usual phase space vector. Very nice thing we found is that the evolution of the dark matter number density equation that we need to know is precisely the same as that of particle. So this is a huge relief for me when we first found this, because otherwise I don't want to spend like 1 year, 2 years developing this formalism for gapped continuum, unless like we already found gapped continuum, right? So which means I can just use what we developed for just dark matter particle, and it's for 2-to-2 scattering case. So
Could you show the previous slide for particle number then?
So
how do you know that it follows the Boltzmann distribution?
So we derive Boltzmann distribution for gapped continuum, right?
You derive.
Yes, that's what I showed.
Sorry, I didn't.
Yeah.
Can you repeat again?
So starting from free energy, why do I care about this free energy and thermodynamics? Because Boltzmann's equation is basically thermodynamics, right? It's not a deep thing. Just you have to. That's why you have to do equilibrium thermodynamics. And
Okay, so F
Yeah.
is distribution of.
Yeah. So the crucial is that So now we understand the role of the spectral density. So now you can define this free energy using this spectral density. So the additional term is this. For particle, this is delta function.
No. F. You just done the distribution F, which looks like Bose-Einstein or Fermi-Dirac distribution, right?
I mean, this one, in the end, like this Fermi or Bose is not so important. So this is just Boltzmann. The first term is dominant.
No, I mean, the gap continuum is weird, guys. So I was wondering
Yeah.
whether it follows the usual distribution function. It can be something different.
From the quantum state point of view, yeah, it does.
So you say there is
Yeah.
one option.
I mean, it's not even a question whether it's a Bose state or it's a continuum state or resonance state, doesn't care. Yeah, I see. Okay. So you see that it's not very difficult.
Oh, that part is.
This part usually we don't write down for particle because this one will be immediately removed because of that.
No, I was not.
Just from point of view
Yeah.
as a state, a particle,
Yeah.
then we can obtain the same distribution, right?
Mhm.
Yeah.
Yeah. The Bose-Einstein
Yeah.
statistics or Fermi-Dirac
Yeah.
statistics.
Even though we don't think
Yeah.
that is a particle. Yeah.
Yeah.
Mm.
So yeah, now I'm teaching undergraduate STEM for
Mm.
4 years. Like this part my undergraduate students can follow and do summer research. So okay, so we do this, and then the nice thing is in the end, like for me, I want to do phenomenology. I don't want to work on some formal theory that formal theorists are not interested in, right? So in the end, this is what you need. So basically, you see how freezing happens. So maybe I should tell you this. So this is the mass gap. So when temperature is larger, the dark matter should still remain in this continuum can be produced, right, from the standard model. So they are in the equilibrium. But if temperature goes below this mass gap, then things happens, right? So annihilation rate drops exponentially, right? Because mass gap is now too larger than temperature. You cannot thermally produce it. So this is the freeze out. This is the version of freeze out for the continuum. So this mass gap is important. Even though this is the mass, if this is term of spectral density, right? And then the Boltzmann, because as time goes in the universe, like temperature drops out, and then this also spectral density will go down towards the mass gap. Because among the continuum state with different mass, they can, if there's an interaction, they can go down to smaller mass gap. So this is the story. So now let's, how much?
think no, it's fine. Before I don't know 6. I don't know. No, we don't have very strict
No.
the cutoff. So
No, I remember I gave this seminar at Irvine, and that's right after COVID, and their first seminar after COVID, and then people asked me questions, and we spent like 3 hours together.
Okay, then 4 hours.
But then they invited me, and we wrote a paper together. So you have to do that if you want.
Okay.
So I ended the writing. Okay. Oh, maybe I quit. So let's have a specific model, G-portal model. So this dark sector has to be stable, right? So we just, as usual, we just put Z2 symmetry. So you can do this to continuum as well because it's on the field itself, right? And then what you do is, so this one is the dark sector, get continuum is the dark matter, our dark matter with Z2 symmetry. And then how do we make it G-portal? We introduce this chi, which is SU2 doublet, and then this covariant derivative of this chi has a Z boson. And then there's an interaction between this dark sector and chi and Higgs. And once Higgs gets fab, like there's mixing. But basically, we make this chi heavy, so in the end, you integrate out this chi in the effective Lagrangian.
So gap continuum can be fermion?
Yes, sir. Yeah, or vector or anything, or tensor.
Sorry? So gap continuum can be fermion state. I'm sorry, but
Yeah.
They are all boson, right?
I mean, in this case, they don't. Put
Yeah, yeah.
No, he just asked.
I mean,
Yeah.
gap continuum, this, how we figure out
Yeah, it's the commutation.
yeah, that's right.
Yeah, but here.
I mean, boson is easy to think, but
Yeah. But here, scalable. That's why I used this as a main example. And then this chi is not the not the continuum. It's a particle, but it's a heavy, and then there's this interaction. And you integrate out, and then okay. So I told you like there's mixing, so that's why this guy is standard model singlet, dark sector. So it doesn't directly talk to Z boson, but because of this interaction and this chi talks to G boson, so that therefore you get the interaction. So effective Lagrangian, this is like the same thing. What happened to my okay, so so this is basically a model, and I want to show you direct detection suppression. So basically, this sin alpha is basically mixing coupling. So, and you from this one you get the spectral density as I said before, and also we derived that the spectral.
So, out of curiosity, so you
Yeah.
just wrote down this Gauss W function, right? And then is
Yeah.
this your only one found? There could be some other.
For software, we only know one. But for discrete term, there are a couple of things that you can put this specific form and then you can do it by hand, compute things. Otherwise, things become numerical.
When you say mixing between what?
Yeah. So mixing between how do you get the Z total? So this phi is singlet, standard model singlet, dark matter. And then the way we couple to this is with coupling with the chi and H. If you see Higgs get fab, this will mix each other, right?
The continuum can mix with the particle.
Yes.
Mm-hmm.
Yeah. If you want to think about 5D language, you have a bulk field and the brain localized field. And then the brain localized part mix with the brain localized particle. Yeah. So in the 5D, it's simple. If you translate it into 4D, it's getting complicated. Yeah. So yeah, that's why you have mixing parameter enters. And when you have spectral density, I told you that the Boltzmann suppression goes so as time goes out, the spectral density becomes getting closer and closer toward this mass gap. So the shape of this spectral density near the mass gap is very important, at the very close to mass gap, because that enters into CMB calculation and many cosmological constraints. So that actually we have an analytic form. So you can prove that this very close to mass gap mu0 spectral density looks like this. This is true for any continuum, vector or fermionic continuum as well. And so in the end, first I want to say this is the effective Lagrangian of G-portal dark matter. So now you integrate out chi. So what you left is this continuum stage and then this coupling times square alpha times G boson. And then this is the plot. So this is kind of money plot. So usually, if this dark matter is particle instead of continuum, the direct detection limit says that this coupling sin square alpha cannot be larger than this. So direct detection will rule out all the parameters here. Otherwise, like you would have already discovered it in the direct detection. But if it's in the continuum, direct detection limit goes like here. So you are allowed. And what is this red line? This is the case where you can the 100% of the Rayleigh abundance of dark matter is explained by our dark matter model. So there are parameter states where this is allowed. And the BDN also gives some bound, but already that below here it's ruled out, but above it's fine. And the red bound is there. But the point is that compared to this is just coupling, right? Not cross section. So not the scattering cross section. So this coupling is like huge order of magnitude. It's allowed. So that's why the WIMP miracle is allowed for continuum.
So it's a G-portal particle case.
Yeah.
So the mu0, you assume the mu0 was the mass of this particle.
Any range order of magnitude within mu0. Yeah.
Okay, then what's the mass of a dark matter particle?
Yeah, around mu0.
Okay.
Yeah. You can change it by factor 10 and doesn't change anything. I mean, that's why G total is that basically. Yeah. I mean, there's some.
Number is say 1 kV and. I'm wondering whether
I'm looking at mu0 below, right? If you go to a certain region, direct detection is fine.
Yeah, I mean, sure. I mean, the mu0 shouldn't be the. I mean,
Yeah.
you may think of it as a mass of the particle comparing.
Yeah. You have,
In general,
you cannot
in
compare.
continuum
Yeah.
picture, I mean, my dark matter particle could be heavier. I mean, as you saw.
Oh, yeah, but
So I don't think it's.
But spectral density, typically we have this, it's not just go infinity, it has some peak from mu0 and then goes down, right? So this
I mean,
is like
what I'm thinking is that may correspond to some heavy particle.
Yeah.
Can I have some heavy particle behaving like this?
No.
And get,
Get continuum is completely different from heavy particle.
let's go to the.
You mean this?
Yeah,
but this is the region.
Okay, so we have
this
that
is-
behavior.
this is- WIMP is the- WIMP is the WIMP is the weak scale. So if mu0 is weak scale particle, then forget about it. It's all ruled out.
No, that's triggered. But
Yeah.
thinking whether any particle thing,
So you-
particle model which can
WIMP-Zilla will be fine.
Yeah, sure. I mean, something like that. Yeah.
WIMP-Zilla, but that's not in the weak scale.
It doesn't matter.
Yeah. I'm not saying that.
I mean.
Yeah, I'm not saying that.
The particular thermal relic diagram, right?
Yeah. So
Is this really unique for continuum, or there can be some particle model which can mimic this?
you can do mimicking, like you can do artificial intelligence, right? Stack of lots of particles
Okay.
looks like that effectively looks like continuum, right?
Okay.
But then you ask why this looks like this and so on. You have no idea. But
But I would ask, I would say,
well-
why? I mean, I can mimic from the particle point of view. Then
Yeah.
why do I have to have a continuum?
yeah. So let me answer.
Okay. Anyway, this is philosophical question.
So philosophy, but we get this continuum just from
Yeah,
this
it's
simple
nice.
Lagrangian, right? It's elegant. So you like artificial intelligence, then why do you even thinking about hierarchy problem or any particle physics? But dark matter, okay, fine. But here I'm not talking about fine-tuned model. It's a generic model.
There are two specific phi 2 and phi 1. Which is the dark matter? Which one is the dark matter?
So these are all dark matter now. So there's coming, this all come from this mixing. Shoot.
So phi is complex field.
Yeah. So you have this mixing. Yeah. So in the end,
One
Phi
can
1
decay
and
into
phi
other.
2. What's what?
and then you say one of them is phi 1 and the other one.
One can decay into other.
Yeah.
Like then if it's like inelastic scale.
Yeah. But no, what I'm saying is, okay, I see.
It's phi
So phi 1 and phi 2, what I'm saying is that they have a mu scale, right? So that's mass parameter, right? But a priori, there's no mass, on-shell mass. So their one will have a mu scale, I call it mu1 scale. The other one will have a mu2 scale. And a priori, they don't have to be same, right? This is the, yeah.
Oh, you have two phis.
I mean, even if it's the same field, like you have a mu1 scale, mu2 scale, and if they are same, you could call mu, but they can be different, right?
Because of integral.
Yeah.
Yeah.
Because there is no on shell. That's the complication of the continuum.
I have one question concerning the freeze-out process,
Mhm.
which I think is on your slide, but you mentioned it much. So
Mhm.
you have this whole ensemble of dark matter states in the end,
Mhm.
and so the heavier part is dropping out of equilibrium at some point, but then you have interactions of
Still within this, even out of equilibrium, still the heavier continuum mass parameter state can decay into lighter ones.
Okay, so they decay into lighter states and standard model particles. So
And
the
yeah,
real, so they are more and more.
I mean, heavier
states.
heavier continuum state goes to, it's a misleading heavier lighter, but heavier continuum mass goes to lighter continuum mass.
Lighter state.
Plus, if it's G total, G go to E plus E minus or whatever, U plus E minus.
Okay, so the real freeze out is basically happening only when you reach the lightest state above the mass gap.
No. But
so what I meant was this diagram, you have the mu1 to mu2 standard model.
but basically, this annihilation rate, the standard model drops down, but the decay still happens even in the later stages, even after freeze out.
Decay or what?
Decay of the higher continuum mass parameter state of the continuum dark matter going to lower.
Freeze out is the
Freeze out is not that. Freeze out is between standard model and dark matter. Right?
Is that between the origin of the CMB and BVN line of it, like this decay of mu1 going to standard model and mu2?
Yeah, so that's, you saw like a CMB bound already in the plot, right? So if that still happens in the later stage, right? Then there will be photon if it decays some standard model which is charged particle electromagnetically, then this will disturb the CMB, right? CMB photon, reionized hydrogen and so on, right? If it's energetic. So that means that yeah, that is the part of my talk. But thanks. After direct detection, but let me go there. So you want this decay happen very quickly before CMB. Otherwise, which means that the coupling has a lower limit instead of upper limit for direct detection, so that near the CMB, most of them will live near the mass gap.
I was confused. So mu1, mu2 are the two different views of the same continuum.
Because they don't have to
Okay, so
have the
you
same.
can have
anything.
larger mu state and smaller mu state.
Yeah,
so
that-
larger mu state can decay to
That's what
smaller
I
mu
mean.
state.
Yes.
Okay. So that has to be suppressed.
Yeah, that's what I told you.
Okay, good.
So I mean that's why you have this CMB limit. CMB limit means that this coupling sin square alpha has to be above this. If it's below, then it decays too slowly. Then eventually it will be ruled out by CMB photon. Okay. So the interesting thing is that the allowed region is where the 100% radial abundance can be explained by this dark gap continuum. Yeah.
So that could be unique. No.
Is this modifying the velocity distribution of the dark matter anyway? Have those decays?
Little bit, but we do some estimation, and it's not changing too much that we have to worry about it.
Everything is determined by states directly above the mass.
Yeah, but some detail will be different.
In the GV order, the free streaming length is not. Then after the dark matter, the lightest state, that is also in GV order. So if you're talking about the free streaming length of dark matter.
Yes. No, what I mean is you have a non-thermal process, or you have a non-equilibrium process by having heavy states decay into a light state and standard model states.
Yeah.
So that can give my light state an additional
Boost.
kick.
Yes, but that will ultimately affect the structure formation, like through free streaming length. I mean, if you are producing these heavy lightest particles after very late temperature or late time, it can affect the free streaming length, like free streaming length of dark matter.
Yes, for example.
And for GV order, I think it's safe.
No, I was just thinking about the velocity distribution, things like is dark matter in net mass regime? Does it move faster? Does it have different behaviors?
Because of the decay, that was Thomas asking. Yeah.
I mean, there's study
Yeah.
for the non-for freezing dark matter, how this velocity distribution.
But at the end, like this goes close to very close to mass gap. So
So the
that's the
picture shows
resolution.
that basically BBN exclude the scenario.
No, BBN is
So
limited.
what's the BBN now?
BBN is like BBN is that this region is excluded.
Below is excluded, not the above.
Yeah. Yeah. Otherwise, I wouldn't give a talk. Right?
Yeah, sure.
And let me tell you one more thing, and then I think that's very important. So I said that the direct detection is suppressed a lot, right? Because like it's a non-relativistic quasi-electric scattering, right? So that there's no huge energy. And I said that in the end, like at the later stage of the universe. So now, like everything.
Sorry again. So why lower region is allowed, forbidden? So for smaller mixing is dangerous.
So BBM means basically this should happen, and if continuum is like still there and this decay happens, right? Then basically the BBN will be interrupted,
So
right?
if alpha goes to 0, it is forbidden.
So if you have a very long-lived particle and if it decays during or after BBN, that can enhance the number of light events. So it has to decay much before
Okay.
BBN. So that
Okay.
Yeah. Yeah, but then the answer, and then in the end, like CMB bound is much more important than BBM bound. But I put it just because.
So this thing is so alpha smaller than that is allowed.
alpha
Forbidden
smaller than that
because
means it decays
decays
after
after BBN.
So like why this is happening this, like numerically speaking, so there's a mu1 and mu2, right? And the difference cannot, I call delta. Delta cannot be too much because in the end, the later stage, Boltzmann suppression, so and the decay, so everything will be close to mass gap. So in the end, like if you solve this numerically, it's very small number, and Q is the center of mass energy for this collision. And then the cross section, you have to remember integrate over this spectral density. That's important. So basically, the continuum quasi-elastic scattering cross section is compared to the particle with mass mu0, has this delta plus q over mu0 to the power 1. R is just in 1/2 if you do 5D model. But for many different 4D model, I don't know, but it shouldn't be that different. But delta is 100 kbps and numerically computed, and Q is for typically non-relativistic case 1 kb. So it means that this is, if you put one R to be 1/2, then this is like 10 to the minus 9 suppression. The direct detection bound, there's huge suppression. So that's why this gap continuum is still allowed for G portal. Otherwise, G portal is very tough for dark matter model now. So as I said, like you have to go into the spectral density is whole this, but the allowed energy is only very small near the end, such that this is more like a sum rule. So this is hugely suppressed. And this is relevant for the collider. If your collider energy is not enough to produce the mass gap, that's why the rep bound is for this G-portal model is so negligible. But in the future collider, if you have a huge energy compared to mass gap, this kind of suppression factor is go away. So then you can look for interesting signal in the future colliders. Yeah, I don't know when that will happen. And also you can look for different recoil rate for different signatures. And also the nice thing is that still this 10 to the 9 suppression sounds like, is it, forget about it. No, actually, nowadays the direct detection limit goes almost toward the neutrino flow. So this will be tested actually. Very close to neutrino flow. So I think I Indirect detection, okay, so for scalar dark matter, it's not very important, but since there is no continuum state in the final state for indirect detection means dark matter ionized in standard model. So you don't integrate over spectral density, right? So therefore, there's no this continuum suppression that I showed you. This is more like a particle case. And the later state view, anyway, everything is close to mass gap. So this is close, really like the particle case with mass gap. So for fermionic dark matter, vector continuum dark matter, maybe indirect detection plays the role, but for scalar, we found it's not important. And the rate decay is what I said. So eventually, this whole spectral density moved towards close to this, right? You can understand. This is what I showed you. So, and the colliders, yeah, I hope one day we can reach into some energy, but maybe in the linear colliders, for example, in our model, like you can look for all this one continuum going to the polar continuum with cascade decay. This can be seen in the future collider. Not for this talk, but if you make the top partner as a continuum, you will see multiple tops in the future collider. For this one, no tops, but so this is something work in progress with Stephen and Maxim Perlstein. And these are like briefly, this is the model of fermion get continuum and for the vector. So here, like indirect detection actually, for the vector is important. So it rule out certain parameter space that explain 100% of the dark relic abundance. But there are many parameters allowed in the weak scale. So in summary, the gap continuum dark matter is well. So as you said, maybe with many particles, inelastic particles with weird things and weird cancellations, you can make it similar to this model. But continuum is a very simple way to do it in the field theoretically without doing artificial intelligence. So this is phenomenologically motivating also because direct detection bound is evaded and you can do many interesting things. So basically, this is we call like changing particle with continuum, so weak miracle. But but there are many different possible models, and you don't have to focus on this weak scale. You can actually look for very light dark matter scale, and there are many interesting things to do. And also, you can do conformal freezing. The CFT phase eventually moved into this gapped continuum phase. Then we have this 5D calculation toy model, so you can compute that. And so that's what I'm working with Seung and my student Yunari. And so anyway, so continuum phenomenology is very, I think it's something new compared to particle resonance phenomenology. So I hope somehow I motivate your interest in this topic. Thanks.
Thank you very much. Any question, comment?
Thank you. I have a very some basic question. So, I didn't expect you could have some continuum with mass gap in an explicit model, but you showed such model.
Mm-hmm.
And then, personally, I usually think about this 5D theory as a 4D kind of some 4D gauge theory.
Mm-hmm.
So in your example, can you guess what kind of gauge theory can give you such?
And so still, it's largely the bulk of 5D is ADS, so you need a Lagian theory, and then instead of a hard wall breaking at the IR scale of the CFT, you have so usually IR break means that CFT is spontaneously broken there, right? But and then radion is the dilaton. Here it's very similar, but you change you replace the hardware by this software. So it's like a different way of marginally breaking CFT or the strong dynamics at the IR. Otherwise, the Rajian, I guess, the reason a lot of parties are relevant for ADS QCD, for example, they're also using software ADS QCD people. So in that sense, like it's still like this Rajian description.
Yeah, but you know, the
Gauge theory is
I mean, you know, you have a very almost continuous. I mean, basically, you call continuous
spectrum.
spectrum, right?
Yeah. Of course, there is cutoff, so I don't go all the way to the Planck scale because this 5 theory is also effective theory that has a cutoff, right?
Cut off.
Yeah.
All right.
Depending on the model, like there's some where
We can go to.
perturbativity is broken down at some scale. So yeah, it depends on which model you're talking
So
about.
your model for this continuum is by Gopsa et al. Or
No.
your own model? Or?
This is like a kind of a generic software model with some special realization. And this, at the beginning, I was showing how to use superpotential, and the superpotential method was actually originally developed for calculating this RS type of model by Gupsa, and Klebanov. But this one, Mariano Quiroz group actually used this, and we said, let's use this setup. Let's not reinvent similar things.
So for the differential calculation, you use the spectral function derived from Gopsa model.
I mean, this superpotential method.
Yeah.
I mean, don't tell Gupsa because Gupsa say, oh, this is ugly model.
This I don't know.
He say, oh, this is ugly model. Yeah. His
I
method.
don't know the background.
And Klebanov's method. Yeah.
How can I imagine the continuum in the space? If we consider particle, we can think of point. But
Yes. Particle is not. A continuum state is also looks like some point, right? So it's not a stringy thing.
yeah,
Except that for particle, you know what you mean by decaying and so on, right?
yeah.
I'm borrowing the terminology decaying, but
Then we can
I should choose the quotation mark.
then we can define also any classical
Mhm.
physical value to the continuum.
Yeah.
Yeah, such as velocity or
Yes.
momentum.
Everything. Yes. And if you produce in collider, if you produce million of them and look at their mass spectrum, they look like spectral density distribution.
And then for fermionic and vector continuum, there may be some calculation rules such as Feynman maybe. Then if I consider fermionic continuum, then when I calculate with fermionic continuum field,
Yeah.
then can I use a usual U or V spinner? With spectral function.
Yeah, usually I go to the Y spinner, but you can use whichever spinner you want to use, right?
Just using spinner or
Yeah, you can change one to the other always, right?
just adding spectral functions.
Yeah.
Yeah.
But the rules are a little bit more complicated. Yeah, and also vector G-portal model, like we're using some generalized Chern-Simon terms, which you can derive UV theory by integrating out certain number of chiral fermions, make sure that this theory is anomaly free, and so on. Yeah.
At least from the pictures you were showing, the spectral function always seemed to peak very close to the mass gap. Is this kind of is this required somehow theoretically, or it's just?
So we are using this 5D model, which has some kind of ADS CFT, right?
Right.
So in the larger region, you have this CFT behavior, right?
Yeah. I see.
Yeah. But at some point you want to modify this thing. I am modifying.
Sure.
Yeah, I mean, can you have some weird behavior like wiggles, jiggles?
Yeah, of course. And also this guy can mix with some holes here.
Yeah.
Holes here.
So if it was like
Yeah.
less steep the gradient from the
Yeah.
peak to the mass gap, if it was much
Yeah.
more linear, say,
Yeah.
would it give any different dark matter phenomenology.
Yeah, you can.
If near the mass gap it was small.
Yeah, you can do this. Yeah. So actually, I said I work on this top partner as a
Yeah.
kept continuum. There, like of course, you have to mix with other things, and there are some plane locality, and there are other discrete terms. So the spectral density looks like, yeah. I mean, they are continuous. That's the only thing I can say. But
No, I understand.
it looks like
Could be really unique signature of this scenario, right? I mean,
if we can prove it.
oh, yeah, of course.
Yeah, of course, we wish we only.
I mean,
yeah.
I mean, for me, I mean, it's like that. So higher mu state takes the
Mhm.
lower mu state and lower and even down to mu zero. So
Mhm.
this signature will be unique. In
Yes,
this
yes,
model.
yes,
So if there is also a bomb somewhere, then could be different signatures.
yes. So yeah, so these cascade
Mm,
things are very interesting.
But you have to hide it.
Huh?
You have to kind of hide it, right? Like from C to B bounds or something.
But when we cleverly
Yeah.
find this spectral function,
Mhm.
avoiding all the constraint and then see the signature. Like, I don't know.
Yeah, or like
Oh, I see. Out of collider.
yeah,
I guess
at the
those
club.
were there in order to hide from CFD bounds, you want to make the interaction strong.
Yeah, right.
Strong interactions are good for colliders.
Oh, I see. I see.
Yeah, that's
Oh,
right.
yeah.
Oh yeah, yeah, check.
Yes.
Yeah.
You got a nice little.
Okay, or can you have the larger displacement?
The this large
Yes,
displacement.
signatures in Vatsula or
Yeah, I mean, like so actually, yeah, like for some reason I'm working on dark photon business with Continuum, not for dark matter, and then like yeah, you can hide this from dark photon searches, and then actually medical all these kind of things can solve this. Yeah. Yeah, Jonathan Peng was interested in that. Okay.
Any other questions? If not, let's thank speaker again. Thank you very much.
Thank you.
interesting.
Thanks.
So,